In this discussion video, we'll be talking about the squeeze theorem and whether or not we want to use it in problems. Alright, so the squeeze theorem, remember, says that if f of x is less than or equal to g of x is less than or equal to h of x for all values of x that are near some number a, except possibly at a, so possibly at a that they don't need to satisfy these inequalities, and the limit as x approaches a of f of x equals the limit as x approaches a of h of x. So both of those outside functions have the same limit, and we're going to call that L. Then the limit of the middle function, g of x, as x approaches a, is also going to be L. So remember that this is helpful sometimes. It's helpful sometimes with bounded functions. Bounded functions. So those are functions that have a finite range. And usually, these bounded functions are going to be multiplied by something in a squeeze theorem problem. Usually multiplied by something. So let's give some examples of bounded functions. So some bounded function examples. So we've seen 3 examples of these. So there is sine x. Sine x is always between 1 and negative 1. There's cosine x, which is also between negative 1 and positive 1. And tangent inverse of x. Tangent inverse of x. This is in between with no equal signs, pi over 2 and negative pi over 2. And we had seen where that comes from in the lecture videos by drawing the graph. So these aren't the only bounded functions, but they're maybe the most classical examples. Anything with a finite range is bounded. All right, so let's look at some worksheet practice problems. So these are from worksheet 2, problem number 8. Question A and B. So I want to begin by having you try these for about 5 minutes. 4, 3, 2, 1. Pause the video and try these for 5 minutes. Maybe give yourself about 2 minutes for part A and about 3 minutes for part B. Alrighty, so hopefully you did that. Hopefully you paused it and tried these for about 5 minutes, giving yourself a little bit more time for part B than for part A. Let's talk about them together now. So for part A, I'm going to do this in 2 ways. So solution 1, I'll do first. So I'm trying to figure out what the limit as x approaches 0 of sine of 1 over x is. We've actually graphed this function in class. So we can recall that graph, y equals sine of 1 over x. We have graphed this in class. And the graph was, it kind of, on the ends, it oscillates kind of like the sine graph. But as you get closer and closer to 0, it speeds up. The oscillation gets infinite as I get closer and closer and closer. Same thing on the negative direction. It speeds up as I get closer and closer and closer. And there's that sort of thing. And just like the sine graph, the lowest it ever gets is negative 1 on the y direction. The highest it ever gets on the y direction is positive 1. So the limit as x approaches 0, we have seen of this does not exist. D and E, because this approaches every number, I'll just write a hashtag for number, every number between negative 1 and positive 1. It is not just approaching a single finite number. So the limit does not exist. Let's also talk about another solution to this. So what if I didn't remember the graph and I wanted to be able to reason it out? Well, the first thing I might do is plug in. And if I plug in, I get sine of 1 over 0. And seeing the fact that 1 over 0 has the form a non-zero number on the top and 0 on the bottom, it reminds me of our strategy of doing one-sided limits. Okay, so let's do the limit from the right first. Limit from the left will be very similar. All right, so the limit as x approaches 0 from the right of sine of 1 over x. So this equals the limit as x approaches 0 from the right of sine of 1 over. And now I'm going to use my notation. X is approaching 0 from the right, which means it's really, really close to 0, but it's a little bit bigger than it. So I'll put a little plus sign in the exponent. And this equals sine of, when you divide a non-zero thing like 1 by something getting super, super close to 0, that's going to be huge. So the top is positive, the bottom is positive, which means it's going to be infinity. So I've boiled this down to now needing to know, well, what is sine of infinity? So I can draw my graph of the sine function and then just take a look at what happens as my angle goes to infinity. So the sine graph goes through the origin and it ticks upwards like this, goes down, oscillates, ticks upwards again, keeps oscillating. In the negative direction it goes down and then up and then down and then so on. So I want to know what's happening as my angle, as the input goes to infinity. So I need my x value, my input, to be going to infinity. So I'm just going to go along the graph, I would just keep going like this, down and up and down. And as that happens, the y values don't approach anything. So thus, this does not exist. Does not exist because it doesn't approach. Doesn't approach one number. It doesn't approach any number. It just keeps bouncing back and forth between 1 and -1, but it doesn't settle in and get really, really close to anything. So now, if I were to do this from the left, we would get the limit as x approaches 0 from the left of sine of 1 over x. So it actually turns out I technically wouldn't even need to do it from the left. The fact that I know from one of these directions it's d and e will automatically mean that the overall limit does not exist. But let's just do it for practice anyways. So this is going to be the limit. In fact, let me just go ahead and plug in now. This is going to be sine of 1 over, but this time I'll write 0 with a little negative sign to indicate it's a little bit smaller than 0. So we get sine of, and 1 over 0 with a little negative sign, that is going to be negative infinity. It's still going to be a huge type thing because the denominator is getting super, super close to 0. That's why we have infinity. But the top is positive, the bottom is negative, which is making this negative infinity. So now we're going to be letting my angle go to negative infinity. So we're going to be going in this direction along the graph, letting the angle get more and more negative. And as that happens, I keep going up and down, but the y values don't approach anything. So this is d and e also. So thus, my original problem, the limit as x approaches 0 of sine of 1 over x, is d and e. So the moral of this question is, even if I have a limit question where something is bounded, because sine was bounded, it doesn't necessarily mean I have to use Squeeze theorem. All right, so that said, let's move on to part B. The limit as x approaches 0 of x squared times sine of 1 over x. So first, maybe let me plug in. If I do that, we get 0 times sine of 1 over 0. And 1 over 0, this is undefined. So you might be thinking, wait, 1 over 0, that looks like non-zero over 0. Could I do one-sided limits? Sure, I could. There's just going to be a more efficient way. And that is what I want to talk about. So let's talk about some intuition. Okay, so as x approaches 0, as it gets really, really close to 0, we are getting the x squared thing is getting really, really close to 0. It is going to be almost 0. And then the sine portion is going to be a small number, because sine is always between -1 and +1. So when you take something that is getting super, super close to 0 and you multiply it by a small number, the whole thing is getting really close to 0. So our intuition is saying that this limit should be 0. We are going to make this, we're going to show this using the Squeeze theorem. It actually turns out that above, when we plugged in to get 0 times sine of 1 over 0, if your thought was, one-sided limits, if you did the one-sided limits, even to do them, it would turn out that you need Squeeze theorem to actually show what the one-sided limits equal. Alrighty, so let's do the squeeze theorem. Remember, the way we get started with squeeze theorem is we identify the bounded part, and that's the sign, and we set up our inequalities for that. So sine of anything, in this case it's sine of 1 over x, is always between -1 and +1. And then we do the same thing to each part of this chain of inequalities to build the function that we see in our limit. So to build that, I would need to multiply everything by x squared. So let's multiply all these terms by x squared. X squared times -1, x squared times sine of 1 over x squared times the 1. And when I do that, the inequalities stay the same. I don't need to worry about flipping them because x squared is greater than or equal to 0. So we don't flip the inequalities. So we don't flip the inequalities. All right, so now the function that I have in the middle of this chain is exactly the one that I see in the limit. Once I get it to that point, we take the limits of the outside functions. So we take the limit, our limit is x is approaching 0. We take the limits of one of those functions is -x squared, the other one is just x squared. And with both of these, we can just plug in. And doing that, here we get -0 squared, here we get 0 squared. So both of these are just 0. And that is what we're hoping for. We're hoping that they're the same. So since these are the same, since these are both 0, by the squeeze theorem, that tells me that the limit as x approaches 0 of my function, x squared times sine of 1 over x, is also 0. If we tried to use squeeze theorem on a problem and we set up a chain of inequalities and we took the limits of the outside functions and they weren't the same, that means either we did something wrong in our computation, or maybe the squeeze theorem just doesn't help with that question and I have to do something else.